Okay, so here's again this expression that we just derived. It relates the final energy of the photon after the collision to the initial energy of the photon before the collision, um, to the angle, the scattering angle of the photon, and the mass of the particle that it scatters off of, and when Compton did this, he did this off of an electron. Okay, and here I've just rewritten it. Okay. And one thing that we'll learn in a few lectures is that the energy of a photon is equal to the product of two constants, Planck's constant h times the speed of light c divided by the wavelength. Okay, so then if we basically plug that in for E and E prime, what we get is that, and simplify, is that we can basically cast this relationship, the Compton relationship, in terms of the wavelength of the scattered light. Okay, and there we go. That's the final sort of the key expression that from this derivation of Compton's experiment. Okay, so it's just the first thing to notice is that the wavelength of the scattered light is not the same as the incoming wavelength of the light. Okay, and it depends on which angle you look. So remember, let's just remind ourselves of the geometry. We have a photon coming in, hitting a particle of mass m. Again, Compton used an electron, and then the photon goes off at an angle theta, and the electron scatters at an angle phi. And what we're basically looking at is the wavelength of the photon that scatters compared to the wavelength that we started with. Okay, and again, it depends on which angle you look, how much that wavelength changes. Okay, let's look at some limiting cases here. Now, if we make theta equals 0, that corresponds to the photon coming in along the x-axis, and it leaves along the x-axis, and that basically says that it didn't scatter at all. Okay, and so this equation tells us this term becomes 0, and this equation tells us that the outgoing wavelength is equal to the incoming wavelength, which makes sense because it didn't scatter. Okay, so now let's think about when theta equals pi. In that case, the initial photon comes in from the left, and it scatters off the electron and comes straight back in the direction from which it came. Okay, so in that case, cosine theta equals to -1, and you have the largest shift that you can have in the wavelength. So the difference between the outgoing and incoming wavelength is equal to 2hc over mc squared. And finally, if you look at the case where theta equals pi over 2, that corresponds to the photon hitting the electron and bouncing off at a right angle. Okay, and so cosine theta equals 0, and so the difference in the outgoing and incoming wavelength is equal to hc over mc squared. Okay, now does this all make sense? Well, since the wavelength is inversely proportional to the energy, as I wrote here, okay, then if the photon imparts momentum to the electron, then that has to reduce the photon's energy, which corresponds to shifting to a longer wavelength. And so what we see, right, is that when the photon hit on, basically, and I should draw the, in this case, the mass will move that way. Okay, and in this case, the mass will move this way. Okay, so in this case, you're imparting the biggest momentum kick to the electron, and so the light that comes back has to be shifted by the most to longer wavelengths. Okay, to longer wavelengths. This is always going to be positive, so you're always going to go to longer wavelengths because you reduce the photon's energy by imparting momentum. Here you don't lose as much energy, but you still lose some in giving the electron some momentum.